Please confirm you can see the presentation. Hello?
Yes, sir.
Thank you. Okay, so let me just briefly recall what we discussed in the last class. We began the discussion on spherical polar systems. Prior to that, we had finished talking about the cylindrical system of coordinates. These are going to be important later when we take up the electrostatic field or the magnetostatic field. So that's why it's important that we familiarize ourselves, because these systems, they will make our mathematical tasks easier. So let me just briefly revise a few ideas we took up. That you have a point P in space, its coordinates in the Cartesian system are x, y, and z. So to come to the point P in terms of the three Cartesian coordinates x, y, and z, you'll have to traverse x this way, y this way, and then z this way in 3 steps. But you can come directly to this point P starting from the origin by traveling along the radial vector in 3-dimensional space. But that does not mean that you can avoid the information that is conveyed by the other 2 coordinates. So to come to this point P uniquely, you need information about the other 2 coordinates. And in this particular case, the other 2 coordinates are theta, the zenith angle, and phi, the azimuthal angle. So theta is measured with respect to the z-axis, and phi is measured with respect to the x-axis. So we follow our usual track, and the first thing that we do, I mean, if you are given 2 vectors, I mean, the same vector in 2 ways of representation, in 2 representations, one is in the Cartesian system, the XYZ system, and the other in the R theta phi system, then there is a way to connect first the coordinates x, y, z with the coordinates r theta phi. That has been done over here. If you look at this little table of formulae, every quantity, all the things on the right-hand side are in terms of the polar coordinates r theta phi. But everything on the left-hand side are in terms of the Cartesian coordinates x, y, z. Okay, the reverse can also be carried out. That is to say, on the right-hand side, in terms of the Cartesian coordinates x, y, z, you can get the 3 polar coordinates r, theta, and phi. Okay, our next task was to convert. So that's the way you convert the coordinate values. In fact, in the tutorial session the day before yesterday, you had to go through a question. The first question was this, converting one set of coordinates to another. Then we come to the idea of converting unit vectors. So the vector R is written in terms of the vector sum of the displacement x, y, and z, vector displacements x, y, and z. And as such, the unit vector r cap can be written like this: sine theta cos phi x cap. I mean, the derivation is just a 2-step thing, so it's no challenge really. And then what about the theta cap unit vector? So like we have done r cap unit vector, the theta cap unit vector could also be worked on. This was the last topic in our previous class where we ended the session. So theta cap unit vector, remember theta cap is in the increasing direction of a longitude starting from the North Pole. So if you are at the North Pole of the Earth, let us say, and then you are coming down from the North Pole towards the equator following a line of longitude, then you'll be traveling along a great circle. You'll be traveling along the circumference of the Earth, so which is a circular path, well, nearly a circular path. And the direction of theta, starting from the North Pole, as here, starting from here, the direction of theta will be along the line of longitude going down like that, which has been represented in this diagram. So if you are going down like that, theta will be tangential to the longitudes as you're coming down from the North Pole towards the equator. So that's how it goes. And so we are able to write theta cap. Theta cap is the partial derivative of the unit vector r cap with respect to theta. That's not a very difficult thing to remember in case you can't understand how you get this derivation. And so, take the unit vector r cap is given over here, so it's not, just take the derivative of theta, of these quantities with respect to theta. Sine thetas will become cos theta, the two sine thetas, and then the cos theta will become minus sine theta, and that is what you have here. Phi does not participate in this differentiation process. Okay, now the next question is, what about the third vector, phi cap? This is the point, this is where we start our discussion of the day. Now, phi cap has been defined on the xy plane, just like it was in the case of the cylindrical coordinate system. Here you have phi cap defined on the xy plane, and phi cap is determined or defined in terms of the sweeping of the shadow of the radial vector r on the xy plane. So if this is the radial vector here going from O to P, its shadow on the xy plane is r sine theta. Now this length, if you sweep it from here, will trace out an angle phi. Sweep it from the x-axis in the anti-clockwise direction, will trace out the azimuthal angle phi. And so that is the way to look at it. Actually, this is going to be just like the way we found phi in the case of the S phi z coordinate system. They are the same things here. So on this plane, theta is 90 degrees. Therefore, sine theta will be 1. If sine theta is 1, remember, r cap is equal to sine theta cos phi x cap, sine theta sine phi y cap, and cos theta z cap. So if theta is 90 degrees, that is pi by 2, then cos theta will be 0 and sine theta will be equal to 1. So that is the thing, that constraint you have to apply in the formula for the unit vector of r. Okay, now let us see. From O to from O to A, you have r1 cap. Sweep it a little in the anti-clockwise direction. A undergoes a displacement to B by a little change in the unit vector delta r cap. O to B is r2 cap. Now between the two of them, you trap an angle of delta phi. This plane has got z equal to 0. Now let's see. R1 cap makes an angle of angle of phi with respect to the x-axis. R2 cap makes an angle of phi plus delta phi with respect to the x-axis. Between R1 and R2, there's a little angular displacement of delta phi. So now let us apply the idea of the law of vector addition. So R2 cap, this vector is equal to vector R1 cap plus delta R cap, this way. Okay. And then delta R cap is equal to the magnitude of R1 cap into delta phi cap. This is the same principle as we talked about in the previous example, as well as in the case of the phi angle in the cylindrical coordinate systems. I'll get to this discussion in a little in some more detail, with some more detail in a supplementary set of notes. Please just wait till then. Now, this thing, R1 cap, will have a scalar magnitude of 1. So this quantity will be equal to 1. Therefore, phi cap will be delta R cap divided by delta phi. Now, delta phi, remember, r cap depends on theta and phi. So, well, actually, it's a fixed value of theta. But you nevertheless, I think just for consistency, you put del of phi here instead of dd of phi. dd phi would mean that r cap depends only on phi, but that is not really the case. It also depends on theta. Anyway, so that is what you have. So when you have sine theta equal to 1 and cos theta equal to 0, you're just left with r cap is equal to cos phi x cap and sine phi y cap and 0 z cap on the z equal to 0 plane. This is what you have. Therefore, phi cap will be equal to the derivative of r cap with respect to phi, which is minus sine phi x cap plus cos phi y cap. Cos phi will give you minus sine phi on taking a derivative, and sine phi will give you a cos phi on taking the derivative. And this you can see, you should be able to realize that it's immediately realize that it's the same formula of phi cap as you got in the cylindrical coordinate system. Anyway, so we have done two things. First is to connect the scalar magnitudes or just the coordinates with one another, coordinates in one set of system, coordinates in one system with the coordinates in the other. We have done that. Now we have connected the unit vectors of the new spherical polar system in terms of the unit vectors of the Cartesian system, x cap, y cap, and z cap. Both, I mean, all for all the three unit vectors, namely r cap, theta cap, and phi cap. Now, our next task will be to write the magnitude of the components of a vector represented in terms of the spherical polar coordinate system in terms now of the Cartesian system. Let us see. Vector A is equal to AR r cap plus A theta theta cap plus A phi phi cap. Okay. Now what is r cap? R cap is something that we have found already. This is the formula of r cap. We put this formula here in place of r cap. In place of theta cap, we put this formula, cos theta, cos phi, x cap, etc. Cos theta, sine phi, y cap. We put that here in place of theta cap. And then in place of phi cap, we put this thing. Thereafter, we connect all the common terms in x cap, y cap, and z cap. Separately, we collect them. So let's see now. You have this AR sine theta cos phi, A theta cos theta cos phi, minus A phi sine phi, this x cap. Then you have got AR sine theta sine phi y cap, A theta cos theta sine phi y cap, A phi cos phi. So all of them are put together into y cap. And for the z-axis, the z component, you have cos theta z cap minus sine theta z cap. There is no contribution to the z component here. And so you just have AR cos theta minus A phi cos, A theta sine theta. So that's what you have. Now you compare this with the Cartesian system. In the Cartesian system, you should have AX x cap plus AY y cap plus AZ z cap. You compare this thing with here because A in both the systems is the same. Therefore, it stands to reason that AX will be equal to this whole thing in the bracket, AY will be equal to this whole thing in the bracket, and AZ will be equal to this whole thing in the bracket, and that's how you write it. AX is equal to AR sine theta cos phi plus A theta cos phi minus A phi sine phi. AY will be equal to AR sine theta sine phi plus A theta cos theta sine phi plus A phi cos phi. And then AZ will be equal to AR cos theta minus A theta sine theta. Those are the three things that we have. I mean, you can square them, add them all together, and you should be able to see that AX squared plus AY squared plus AZ squared is equal to AR squared plus A theta squared plus A phi squared. I'll show that in a supplementary set of notes, but I think you should be able to do it by yourselves. It's not a very difficult exercise, really. Okay, now we look at line, surface, and volume elements. Okay, as usual, it's very important to have a geometric intuition of what is going on here. So we shall begin with that. Here is a point. This is the first point, making an angle theta with the z-axis. This point has got the radial displacement r from the origin of coordinates. You travel a little way forward along the r direction by a little displacement dr. That's your first step. Remember, r theta phi. Therefore, your first displacement must be in the coordinate r. Second displacement must be in the coordinate theta. And the third displacement must be in the coordinate phi. So you have made your first displacement along the radial direction dr. That is, dr r cap. Now, from here to here, you are coming down. What is this length, this curved path traced by the red colored curve? Okay, so first let us go back a little to this curve over here. If this displacement from the origin is r and this angle is theta, then you have shifted by a small angle d theta. And so if this is d theta, then this curved length shall be r d theta. R d theta you have over here. Now, if that is r d theta, then this thing will be r plus dr into d theta. But you neglect that dr with respect to r, and you write this curved face as nearly equal to r d theta. So that is how you write it. So that's your second displacement along the theta direction. Like I have tried to draw over here, these two dotted lines are like the lines of longitude on the surface of the Earth. And so theta is increasing in this direction like that. So that's how you have it. Okay. Then you have the third displacement in the phi direction. Phi goes along, but then phi is defined not in 3 space, but on the xy plane, on the plane z is equal to 0. Therefore, let us look at what is happening down there on z is equal to 0. So here you are. If this is r, then the shadow of the radial vector r is r sine theta on this plane. That radial vector makes an angle phi with the x-axis. A little displacement that way makes an angle d phi, a small angle d phi. If that small angle be d phi, then this curved path will be r sine theta d phi. Okay, but you're not moving along this path or this path, you're actually moving along this path. Since this angle, this path is slightly greater than r, it is r plus dr, you'll have to make an approximation, and approximately that is equal to, this thing is equal to r sine theta d phi. And that is happening along the phi cap direction. Therefore, you write r sine theta d phi, phi cap. Okay. So as soon as you have the 3 line elements, you notice something about these line elements. Theta does not have any dimension, although it has a unit. In this case, you must refer to the unit radian. Although it's common place to use the term degrees, but actually we use the unit of degrees, but radian is the appropriate thing to use. But theta being an angle, in terms of the radian units, it doesn't have any dimension. But you are adding a length displacement here. These are angle displacement, d theta and d phi, but multiplied by the radial vector r, all of them will now have the displacement of length. Sine theta, of course, is a ratio of 2 lengths. That is also a dimensionless quantity. Sine theta, if you recall all right, is defined as the perpendicular upon the hypotenuse of a right angle triangle. Okay, now let us talk about a few important things. 3 surface elements. You have got the line element over here. As soon as you have the line element, you can immediately construct the surface elements. Hello? Anybody has a question to ask? If you have a question to ask, it's better that you put it in the chat. Otherwise, please don't disrupt the proceedings. Okay, so again, it's the usual algorithm to follow: 1 cross 2, 2 cross 3 in a cyclical order, and then finally 3 cross 1. 1 cross 2, 2 cross 3, and 3 cross 1. That's how we go in a cycle. So this is, remember, R is 1, theta is 2, phi is 3. So 1 cross 2, dr r cap cross r d theta theta cap. And which phase is that? We have got a little kind of a wedge over here. I mean, you can imagine this thing as a little section out of a watermelon or something that you have cut out. A watermelon is nearly spherical. You have cut out a wedge out of a watermelon, and then you have cut a section out of that wedge. So this may be seen to be the wedge of a watermelon in the red line and the green lines, the red and the green lines. Okay, so let's see, this is the radial direction, this is the theta direction, and so this side face is what is trapped between those two unit vectors, the side face. So dr r cap cross r d theta theta cap. Let's see, you have got r dr d theta vector. It's an area element. An area element is a vector element. And then you have r cap cross theta cap. R cap cross theta cap, meaning 1 cross 2 will be equal to 3. We shall prove these things mathematically and more systematically soon enough. But I'm just getting a little ahead of the story, and I'm telling you it's the familiar thing. First vector, first unit vector cross second unit vector gives you the third unit vector. Okay, so r cap cross theta cap gives you the third unit vector phi cap. 1 cross 2 is equal to 3. You can immediately imagine that 2 cross 3 will give you 1, and 3 cross 1 will give you 2. Now let us look at 2 cross 3. Theta cap this way, phi cap this way, which means that it's the outer phase that we are worrying about. And this phase is particularly important. We shall soon see how. So this is the outer phase. It is r d theta theta cap cross r sine theta d phi phi cap. Let's see now, you have got r squared sine theta d theta d phi. Theta cap cross phi cap. Theta cap is unit vector 2, phi cap is unit vector 3. 2 cross 3 will give you 1, which is r cap. That's the third unit, I mean the first unit vector that you have. This open outer face is very important for many reasons, because if you integrate this open outer face, you will get the full spherical area. So remember, in flux problems, we'll have to calculate the total flux of an electric field coming out of the total flux, electric flux coming out through a full spherical surface area. So you shall have to integrate this over this area element. Remember, area element means that there will only be 2 Ds. If it's a volume element, it will have 3 Ds. And you can immediately, you should be able to see for yourselves that this area element, when you integrate over the full spherical surface, shall give you 4 pi r squared, which is the total surface area of a sphere. Anyway, we shall do that in detail soon. Okay, the third phase is trapped between vector 3 and vector 1. Vector 3 is this way, and vector 1 is this way. So basically it is trapped between, so it's this top face or the bottom face. Those are that's the third vector, and this is the first vector. So open outer face. So the top face is what you have, 3 cross 1. And you will have r sine theta d theta phi cap cross dr r cap. Okay. So that's what you have, and the unit vector will be the second vector. Phi cap cross 3 cross 1 is equal to 2 r dr sine theta d phi. Okay, volume element is not a very difficult thing to compute in any case. It's just the magnitude of the first unit vector, magnitude of the first displacement into magnitude of the second displacement into magnitude of the third displacement. When you take all the three things together, you will get dr, r d theta, r sine theta d phi, which will be r squared sine theta d theta d phi dr. It's a scalar quantity. I've written something over here, integrate. That's the volume element of a sphere. When you integrate that thing through the whole volume, spherical volume, you should be able to get 4/3 pi r cubed. I hope you know that that is the volume of a sphere. You can do that thing by yourself, but I'll show you how. So remember, this open outer face is very important, and this volume element is very important, because those are the two things we shall be using. When you do Gauss divergence theorem, you will have to carry out computer volume integral d tau over the divergence. So d tau, the volume element, will be this. Okay, now, but before I get into that discussion, those discussions in detail, I will just touch upon this issue of finding out this 1 cross 2 is equal to 3, that kind of formulation. The unit vector of the first displacement crossed with the unit vector of the second displacement will give you the unit vector of the third displacement. That is to say, and also that the unit vectors are perpendicular to one another. They are orthogonal. Okay, let's see. In order to do so, we shall first have to write this thing, r cap, theta cap, phi cap. The three formulae we have over here. Next is, we'll apply our familiar understanding, knowledge of the Cartesian unit vectors, x cap dot x cap, y cap dot y cap, and z cap dot z cap is equal to 1. X dot y, y dot z, and z dot x are equal to 0. Okay, now let us take r cap dot theta cap. Let's see. When you do that, x cap dot x cap will give you 1. X cap dot y cap and x cap dot z cap will be 0. Similarly, y cap dot x cap, y cap dot z cap will also be equal to 0. And likewise, so it's only the x cap dot x cap, y cap dot y cap, and the z cap dot z cap products that will survive. And so what are they? They are sine theta, cos squared phi. Sine theta, cos theta, sine squared phi, minus sine theta, cos theta. That is what you have. So sine theta, cos theta into cos squared phi plus sine squared phi. So cos squared phi plus sine squared phi will be 1, and you'll just have sine theta, cos theta from the first two terms, and then minus sine theta, cos theta. So they will cancel, and you'll get 0. Okay. Next is theta cap dot phi cap. Again, the same principle applies. Anyway, in phi cap, z has no contribution, so you put a 0 in front of z. So x cap dot x cap, y cap dot y cap, they contribute. Z cap dot z cap will anyway be equal to 0. And so basically you will have cos theta, cos phi, sine phi, minus cos theta, cos phi, sine phi, plus cos theta, sine phi, cos phi. So when you put all that together, minus cos theta, sine phi, cos phi, plus cos theta, sine phi, cos phi, they will cancel again, and you'll get 0. So you can immediately see r cap dot theta cap and theta cap dot phi cap are perpendicular to each other, which means that the third relationship will also be perpendicular. Geometrically, that is how it should be, but we shall just establish that in algebraic terms, phi cap dot r cap. So again, phi cap dot r cap, we'll just have to go by the x cap dot x cap and the y cap dot y cap thing, and you'll get minus sine phi, sine theta, cos phi, plus cos phi, sine phi, sine theta, minus sine theta, cos phi, sine phi, plus sine theta, sine phi, cos phi. They will cancel, and you will get 0. That is how it should be. And when you take the dot product of the unit vectors with themselves, r cap dot r cap, just see for yourselves what you will get. This thing dotted with itself will give you sine squared theta, cos squared phi, plus sine squared theta, sine squared phi, plus cos squared theta. So sine squared theta is a common factor in these two terms, and cos squared phi plus sine squared phi will be 1. So sine squared theta plus cos squared theta will again be equal to 1. And likewise for the theta cap dot theta cap thing, you will get, this is what you have dotted with itself. It will be cos squared theta, cos squared phi plus cos squared theta, sine squared phi. That will be cos squared theta. And then the third thing will be sine squared theta. And so that will also be equal to 1. And for phi, it's much more trivial than that. This is just like the phi in the cylindrical coordinate system. you'll have sine squared phi plus cos squared phi dot upon getting a dot product of its own self, and that's also equal to 1. So you can see r and theta are mutually perpendicular, theta and phi are mutually perpendicular, and phi and arc r are also mutually perpendicular, and that is what it should be if you go by what has been drawn in this diagram. R goes this way, theta goes this way, phi goes this way. So that is the direction, the radial direction of the vectors that you can get. So they are all going in 3 different directions. If you were to think of the Earth's surface as a perfect sphere and apply these ideas, then R will be pointed from the center of the Earth out of the surface towards space. That's radial vector. Theta will be along a direction that is tangential to a line of longitude, and phi will be tangential along a line of latitude, along a circle of latitude. So that is what you have. Okay, so we have established the orthogonality. Now we shall just show that the cross products, 1 cross 2 gives you 3. So let's see. R cap cross theta cap. We use these formula over here. This is R cap, this is theta cap. And so when we do that, you have x cap, y cap, z cap, and you have sine theta cos phi, sine theta, sine phi cos theta. And for theta cap, you write cos theta, sine phi, cos theta cos phi, cos theta sine phi, minus sine theta. Let's take the cross product one by one. This is just a little tedious little exercise, but it's not very difficult at all. So you have x cap, then this into this, minus this into this. So minus sine squared theta sine phi, minus cos squared theta sine phi. Okay. Then you will have here minus y cap is minus sine squared theta cos phi minus cos squared theta cos phi. And then finally the z cap unit vector. The z cap unit vector will give you sine theta cos theta sine phi cos phi minus sine theta cos theta sine phi cos phi. There you have these things. These two things will cancel each other. Whereas here, if you look, minus sine phi is a common factor, then you have sine squared theta plus cos squared theta. That's 1. Similarly, minus cos phi is a common factor, and you have sine squared theta plus cos squared theta is also equal to 1. And this minus cos phi into minus y will give you plus y cap. And that's equal to phi cap. If you go by the definition here, minus sine phi x cap plus cos phi y cap, this thing is equal to phi cap. So you have already shown that r cap cross theta cap is equal to phi cap. Next is theta cap cross phi cap. Let's see now. This will be simpler to compute. These are the components of theta, these are the components of phi. You have x cap. So this will give you 0, and this will give you minus into minus sine theta cos phi, minus y cap. This will give you 0, and then minus and minus into minus will give you minus sine phi, sine theta. This will give you z cap, will give you cos theta cos squared phi, and then minus into minus plus cos theta sine squared phi. And so when you have all that, this you will get as theta cap cross phi cap will be equal to this, and then this into this y cap sine phi sine theta, and then you will have cos theta cos squared phi plus sine squared phi is equal to 1 cos theta, and that's equal to r cap. That is what you have. That's the definition of the radial unit vector, r cap. That's what you have. So there you have this thing. And then phi cross r, 3 cross 1. So there you have it. This is phi and this is r, and then x cap is equal to cos theta cos phi minus 0, y cap is equal to minus sine phi, yes, minus y cap into minus sine phi cos theta. So it will be plus cos theta sine phi y cap. And this will be 0. And then z cap is equal to minus sine squared phi sine theta minus sine theta cos squared phi. So when you have all of them put together, this is what you shall get: cos theta cos phi x cap, y cap, cos theta sine phi, minus, and the minus is a common factor with sine theta. Sine squared phi plus cos squared phi will be equal to 1, and that's equal to theta cap. This is exactly the sort of thing that you get this 1 cross 2, 2 cross 3, 3 cross 1 business as you get in the XYZ coordinate system. This is the same thing that you're getting. X cap cross Y cap is equal to Z cap. Y cap cross Z cap is equal to X cap. Z cap cross X cap is equal to Y cap. Okay, before I go to the supplementary set of notes to discuss some of the ideas of spherical polar coordinate system in greater detail, I should just like to touch upon a few things here in vector differential operators under cylindrical symmetry. Let's see what we have here. Remember, I mean, I told you why, earlier also I mentioned to you why we have taken the cylindrical or familiarized ourselves with the cylindrical and the spherical polar coordinate systems. The reason is that soon we shall have to deal with vector fields which will be dependent, which will move around in free space. However, certain vector fields will be easier to work with mathematically when represented in terms of these curvilinear coordinate systems. So for instance, when you talk about magnetic fields which go round in, so you have a current passing through a straight wire. A magnetic field goes around that straight wire in circles. And what you have in that wire, I mean, those field lines will be in the cylindrical symmetry. And as such, when you study magnetic fields, we shall see for ourselves later what I mean. As such, when you study magnetic fields, it will be easier for you to apply the ideas of cylindrical symmetry, namely using only the unit vector S. I'm sorry, using only the coordinate S, not phi and Z. Similarly, when you use the spherical polar coordinate system, a natural physical system is the gravitational field or the electrostatic field. They depend only on the coordinate R, not on theta, not on phi. So it will be easier for you to work with the radial coordinate only and go to a new curvilinear system, go to a new system where you'd be allowed to do that. Unlike in the Cartesian system, if you were to work out the mathematical problems of electrostatics in the Cartesian system, you'll always have to worry about 3 variables, x, y, z. But in the spherical polar coordinate system, you just use the radial dependence. So, I mean, these are the basic formulae we shall apply. I'm not asking you to memorize these things. Usually in the examination, you will be provided a table of formulae of the cylindrical and spherical polar coordinate system for the derivatives only. For instance, you have gradient of psi, divergence of A, Laplacian of psi. Or you have, I mean, the same thing is happening in the spherical polar coordinate system. You have all these things. So a table of formulae will be supplied to you for the examination. I'd just like to draw your attention to a certain symmetry here. I told you magnetic field lines depend only on S in the cylindrical coordinate system, not on phi and Z. And similarly, electric field lines depend only on the radial coordinate R, not on theta and phi. So that's the reason why it will be easier for us to work out the mathematical problems in these new coordinate systems. Remember, all coordinate systems are equivalent to one another, the Cartesian, the cylindrical, and the spherical. Therefore, you can very well work out, not learn all this business of cylindrical and polar symmetry and just work with the XYZ coordinates. You will be making no mistake, no mathematical error in that. It's not wrong, it's just that the mathematical steps will become very long and tedious. That's why, to avoid all that trouble, it's better to go into a new set of coordinates. I'd like to draw your attention. So remember that thing, all coordinate systems are equivalent. You notice these two formulae, the divergence of A and the Laplacian of scalar psi. This is 1 upon S, dds of S, AS, S component only. What did I tell you? That the dependence is only on S, not on phi, theta, phi, and Z. If it is only on the S component, and here also you have the Laplacian, it is 1 upon S, dds of S, d psi ds. Whereas in the spherical symmetry, it is 1 upon r squared, ddr of r squared, then the magnitude of the component along the r direction. Similarly, here you also have 1 upon r squared, ddr of r squared, d psi dr. So you have these two things. Why am I drawing your attention? Notice the square power here, 2 and 2, 2 and 2. Whereas here it is the first power, 1 and 1, 1 and 1. Now I am asking you to think of the Cartesian system. In the Cartesian system, suppose you are dealing with a problem which has got only dependence on one coordinate, say x. Just like here you have got dependence only on s and r. There you have dependence only on one coordinate x in the Cartesian system. If that is so, just like this has been raised to the power 1 here, this, and I have not written 1 explicitly. If you don't write anything, it means 1. S raised to 1, S raised to 1, S raised to 1, and S raised to 1. Here it is R raised to 2, R raised to 2, R squared and R squared. If you were to work with the Cartesian system, it will be like 1 upon x raised to 0 ddx of x raised to 0 ax. Similarly, 1 upon x raised to 0 ddx of x raised to 0 d psi dx. And x raised to 0 will be equal to 1. So basically you will have divergence of A will be del or ddx of ax. That's how you have it. And Laplacian of psi will be d2 psi dx squared, because x raised to 0 and x raised to 0 will give you 1 in both cases. So you can see in the Cartesian, so there's a pattern that you should be able to recognize in all this. In the Cartesian system, it's something like raised to 0. In the cylindrical system, it's this first variable s raised to 1. And in the spherical polar system, it is r raised to 2. So 0, 1, 1, and 2. In a proper logical arithmetical sequence. Okay, so I shall now go on to the supplementary set of notes. I'm stopping the sharing here. Please bear with me. I'll just these are the supplementary set of notes. I've written the phi cap component of the line element. You remember these were the points we discussed for the cylindrical coordinates in the last class, additional points. There was some error in my hurriedly written notes. I told you to make a careful note of that. This z cap, this z cap, and this z cap should be s cap. So make a careful note of that. Okay. Now we go to the spherical polar coordinate system. So slight details are required. So let's just try to see what I mean. So this will, I'll just quickly discuss these things with the help of these supplementary notes. So let's say what you've got in front of you is the Earth, the surface of the Earth. Well, I should have drawn a proper sphere. This is just a hand-drawn sketch, so it doesn't look like a sphere. But then that's not too bad either, because the surface of the Earth is not perfectly spherical anyway. So let me just try to explain a few things. Here theta is equal to 0. This is a sphere that you have drawn on the surface of the Earth. The radius of the sphere is r, and I have written over here. So theta is equal to 0. You come down this line of longitude. As you increase the value of theta, r will be along the radial vector going out like that way and coming down the line of longitude along the theta cap, along the coming down along a line of longitude. Your direction will be tangential to this circle, and that direction is the same direction as the unit vector, as that of the unit vector theta cap. And likewise, if you go along this path, you'll be tracing out a line of latitude, and so that will be phi cap. However, there's a major difference between the Earth's coordinate and this. In the case of the Earth, theta starts from the disk plane, the xy plane, the base plane, and goes up this way. That's why on the equator, theta is equal to 0 for longitude, 0 latitude, and the North Pole is 90 degrees. So if you say that you're 90 degrees north, it means that you're standing on the North Pole. Okay. Now, let us see how theta is defined. If you are supplied the value of r, starting from the origin, you can go in any direction, and then you'll come to the surface of a sphere. I say that make an angle of theta with respect to the vertical axis. So with that fixed angle, that constraint, if you travel out, it'll be on the rim of a cone. I'm sorry, it'll be on the inclined surface of the cone. So making an angle theta, if you travel out a distance r, it could be anywhere on this circle, this particular latitude. So that's what I have written over here. For a value of theta, vector r traces an inverted cone. So this is an inverted cone, as you can see. This is an inverted cone, and so you'll get many such inverted cones. Okay, I've also mentioned something over here: latitudes defined by theta. Similarly here, longitudes defined by phi. This is the xy plane. Phi is defined on the xy plane. On the x-axis, phi is equal to 0. On the y-axis, phi is equal to pi by 2. On the xy plane, theta is equal to pi by 2. Starting from 0, if you come down here, you would have traversed an angle of pi by 2. Theta is equal to pi by 2. And the equator is on the xy plane. So I hope you have understood this discussion. Now, I will just briefly mention a few points that we discussed, that with only r known, the position could be anywhere on the surface of a sphere, okay, which has a two-dimensional geometry. Knowing both r and theta, the position could be anywhere on the circular rim of an inverted cone. It could be anywhere here. Any kind of a cone, depending on the angle depending on the value of theta. Okay. The vertex of the cone is at the origin, and its circular rim traces out a latitude, which is one-dimensional. So, 2 points of information missing in the first case. You know only r. Therefore, your uncertainty is two-dimensional in nature. 1 point of information missing. That is phi. Knowing r and theta, your uncertainty is one-dimensional in nature. And when r, theta, phi, all three are known, the position, there is no uncertainty. Uncertainty is zero-dimensional in nature. That is what you should say. And that is to say, you have hit the point exactly where you're supposed to be. So with r, theta, phi known, the position is known precisely where a longitude set by phi intersects a latitude. This is a longitude, this is a latitude. Set by theta, they intersect. Okay. Now I'll just have a little more detailed discussion on the unit vectors theta cap and phi cap. Some geometrical intuition is necessary. Let's see. If you have a clear geometric eye, then these curvilinear coordinates are non-challenge. But that is what you need: a geometric eye and an imagination. So let's see now. The tip of the unit vector r cap sweeps out an arc length AB. Okay, so you're starting from here, theta equal to 0, and unit vector r cap starts from the origin and comes here with length equal to 1, magnitude equal to 1, but direction could be anywhere in space. Theta equal to 0, you come down over here, this way, A to B. Okay, so what is the arc length AB? Arc length AB is equal to line OA, line segment OA into delta theta. AB is equal to line segment OA into delta theta. And what is line segment OA? That is equal to R1 cap. That magnitude is equal to that thing. But then R2, this vector, by the law of summation of vectors, is R1 cap plus delta R cap. This line segment AB, you can see from the diagram itself that line segment AB will be smaller in length compared to arc length AB. Arc length AB comes on the curved path. Line segment AB goes straight along the straight line. So line segment AB is less than the arc length AB. But when theta goes, delta theta, this small angle goes to 0, then the curved path will slowly become, in the limit of delta theta going to 0, the curved path will tend to become equal in length to the straight path AB. So arc length represented by this arc will tend towards length of the arc length AB will tend towards the value of the length of the line segment AB. Delta theta going to 0, this is what will happen. So when delta theta is equal to, well, tends to 0, not equal to 0, line segment AB will tend towards, the length of the line segment AB will tend towards the length of the arc AB will tend towards the line segment AB. So that is what it is. So AB will become equal to delta R cap. Now delta R cap is equal to, now AB is equal to R1 cap delta theta, magnitude of R1 cap delta theta. Therefore, when delta theta goes to 0, AB, which is going to be equal to delta R cap, will be equal to R1 delta theta. Therefore, delta R cap is equal to R1 cap delta theta, theta cap, in the limit of delta theta going to 0. Thereafter, you can follow the familiar calculations in the main set of notes. So that is how you do it. What about the unit vector phi cap? Phi is defined on the xy plane where theta is equal to pi by 2. The properties of the unit vector phi cap in cylindrical coordinates s phi z hold true for phi and phi cap in the r theta phi system. Whatever you have done in the cylindrical coordinates of the angle phi will be the same for the angle phi in the r theta phi system. So on the plane, theta is equal to pi by 2. Theta is equal to pi by 2, meaning the xy plane. Theta is 0 here. When you come down to this plane, theta would have traveled through an angle displacement of pi by 2, 90 degrees. So on the plane, theta is equal to pi by 2, and vector r and r cap behaves like vector s in the cylindrical coordinate system. Okay, now we shall just look at a few extra details, direction of r theta and phi. R cap, theta cap, and phi cap. Here's a diagram that shows R cap going this way, theta cap going along a longitude, and phi cap going this way. Here's a very important point. I will touch upon that thing. You notice something, whereas you follow this point extremely carefully. R can start from 0 and go out to anywhere it wants to. Up to infinity, it has freedom to travel. Phi can only go in a cycle, and that full cycle for phi will be 2 pi. Phi goes round in a full cycle of 2 pi. What about theta? Theta goes in, starts with the value 0 and ends at the value pi by 2. I'm sorry, I made a mistake. Ends at the value pi. Theta will start from 0 and theta will end at the value pi. This theta equal to pi by 2 is for the base plane. Here theta is equal to pi. Okay, so we shall see why we go up to theta equal to pi. In due course, so I shall discuss that. First, let's just discuss certain direction ideas. I told you that as opposed to the x cap, y cap, z cap coordinates, which are frozen in space, the unit vectors, the Cartesian unit vectors are frozen in space. They do not change direction at all. However, in the curvilinear coordinates, both in the s, y, z system and in the r, theta, phi system, the coordinates can change direction because the coordinates are functions also of the unit vectors are functions of the coordinates. So vector r cap is equal to sine theta cos phi x cap, sine theta sine phi y cap plus cos theta z cap. Now let's see, when theta is equal to 0, theta is equal to 0 over here. If theta is equal to 0, sine theta will be 0. So regardless of the value of phi, doesn't matter. Cos theta will be equal to 1. When theta is equal to 0, z cap will always be, r cap will always be pointing along the vertical direction, z cap. When theta is equal to pi by 2, 90 degrees, you have come on the equatorial plane, the base plane. R cap is equal to cos phi x cap plus sine phi y cap plus cos theta will be equal to 0 when theta is equal to 90 degrees. So now you have this thing behaving just like the s cap unit vector in cylindrical coordinates. Okay, so when phi is equal to 0, you are on the base plane. So when phi is equal to 0, r cap will be pointing along the x cap direction. When phi is equal to 90 degrees, r cap will be pointing along the y direction confined to the base plane when theta is equal to pi by 2. Let's look at certain properties, certain angle changes for theta cap. Theta cap is equal to cos theta cos phi x cap, cos theta sine phi y cap, and sine theta z cap. Okay. Here's an important point. When theta is equal to 0, this will be 1, this will be 1. Sine theta will be 0. So when theta is equal to 0, theta cap is equal to cos phi x cap plus sine phi y cap. It will be just like r cap on the theta equal to pi by 2 plane, meaning that it will depend on the angle phi. For instance, if you are here, and angle phi is angle phi is 0 degree, then tangentially it will be pointing along the x direction. If angle phi is 90 degrees, then tangentially it will be pointing along the y direction on the North Pole at the top of the sphere. That is what happens. Okay, and when phi is equal to 0, as I said, theta cap will be equal to x cap, and phi is equal to pi by 2, theta cap will be equal to y cap. Now, when theta is equal to pi by 2, this is also something, what's the direction? When theta is equal to pi by 2, you can immediately see that this arrow will drill down vertically downwards along the minus z direction. This arrow, which is tangential to this curved path, will be drilling down through the xy plane. Let's see, when theta is equal to pi by 2, if theta is equal to pi by 2, this and this will vanish. Sine theta will be equal to 1, theta cap will be equal to minus z cap. And here is what I just said. It will be going downwards on the xy plane, drilling downwards on the xy plane. Finally, for the phi cap unit vector, these are things you have done. Phi cap is defined on the xy plane for theta equal to pi by 2. So minus sine phi x cap plus cos phi y cap. When phi is equal to 0, phi cap is equal to y cap. So I think I made a mistake over there. No, I have not made a mistake. When phi is equal to 0, sine phi will vanish, cos phi will be equal to 1. When phi is equal to 0, you're going this way. So you're pointing in the plus y direction. That's what it says. And when phi is equal to pi by 2, you are here pointing into the plane of the paper along the minus x cap direction, negative x direction. Okay, so that's just some little discussion on the this thing, the direction and certain issues pertaining to some clear idea about how to find out the variation of the unit vectors, the angle unit vectors in the spherical polar system. I'll just show you the scalar magnitude of the vector, just to prove here that regardless of whatever representation you take, the Cartesian representation or the spherical polar representation, the scalar magnitude of the vector should not change. So here we have the three relations connecting the components, scalar magnitudes of the components of the same vector represented once in the XYZ system and another time in the R theta phi system. So the right hand side is R theta phi, the left hand side is XYZ. Now we square all the three equations. AX squared will be equal to, a little difficult, now we have got three terms here, similarly for AY. So AX squared is whole thing. I mean, how do you square three terms? Suppose you are given A plus B plus C whole squared. It will be A squared plus B squared plus C squared plus 2AB plus 2BC plus 2CA. So that is what you have. That's the thing, that you will have six terms in all. A squared, B squared, C squared plus 2AB plus 2BC plus 2CA. Similarly for the Y coordinate and the Z coordinate. So when you add the left hand side and all the terms added on the right hand side, you will see these strokes mean that all the terms that contain the factor of 2, this, all the six terms will cancel, seven terms will cancel from the AZ equation also, and you are simply left with AX squared plus AY squared plus AZ squared is equal to AR squared plus A theta squared plus A phi squared. You can check these things. I'll supply you the notes anyway, so the detailed calculations you can verify for yourselves. But this is not a very difficult thing at all. The main key point is how to square A plus B plus C whole squared. So it is A squared plus B squared plus C squared plus 2AB plus 2BC plus 2CA. Okay. Now, I'll just touch upon certain approximations we have made in the displacement, the theta cap component of the line element. How do you find the theta cap component? So remember, we are dealing with the spherical polar coordinate system. If it's a spherical polar coordinate system, then you have the three coordinates are theta phi. The first displacement will be along the radial direction r. The second displacement will be along the angle theta, and the third displacement will be along the angle phi. So how do you find the theta cap component of the line element? Let us now see. Here's a radial distance O to A, which has a length r and makes an angle of theta with respect to the z-axis. From A to B, you travel by a little displacement dr. Okay. After you've come here, then you are traveling along the theta direction, and the theta direction is BC. But then in a parallel curved path next to it, you have the curved path AD. Both of them are parallel curved paths. So it's quite clear that AD, which is equal to r into d theta, is shorter in length compared to BC, which is equal to r plus dr. Here, r plus dr d theta. Okay. So now let us see. AD is equal to r d theta is the inner arc length along which you are not traveling. You are traveling along the outer arc length, because once you have gone from A to B, thereafter you have to travel from B along the second coordinate, so which is this arc path BC. Okay. So BC is r plus dr d theta is the second step. So it's the R, which is also the outer arc length. Now BC arc length is equal to R d theta plus dr d theta. So you simply put this dr, as it tends to very small values, tends to 0, can be neglected against the R. And so BC is equal to, when you neglect the dr terms, and anyway, you only have to worry about first order derivatives in calculus. That is what you do. So BC arc length is going to be equal to R d theta, and this part dr d theta with two d's will be much smaller compared to a term which contains only one d. Therefore, you can neglect that. Or you can also just look at this formula and say, I'm neglecting the smallness of dr against the standard value, large value of d. R. Therefore, considering only the first order meaning 1d, second order meaning 2d's. That's what you have, considering only the first. So that's how you do calculus, by the way. So arc length BC is equal to R d theta. So that's the second step. R d theta you have here. Okay. Now, the outer arc length, therefore, neglecting this dr, will be equal to R d theta, theta cap, for d theta going to 0. And R d theta, as I said to you, must have the length dimension, because we are already adding it to the first displacement, which dr r cap, which also has the length dimension. Now we will be a little careful for the phi cap component of the line element. What is the phi cap component of the line element? Here, a bit of an attention is required, really. Let's see. First, O to A is radial vector R. Then from there, you have gone to AB, which is dr. Then from B, you have gone down to C, BC. Now you want to make the third step. So as I've written over here, AB dr is the first step. BC arc length. AB is incidentally a line element, whereas BC along this curved path is an arc length, but it's the second step. So BC just now we have argued is R dr, R plus dr d theta. And then the outer arc will be C to D, outer arc, and that's the third step. Okay, so how do we calculate C to D? Remember, now we have to travel through the third coordinate, which is phi, the azimuthal angle phi. If we have to travel through the third coordinate, then the third coordinate having been defined on the xy base plane, we'll have to drop perpendiculars, both from here as well as from here. CD is equal to C prime D prime, arc length CD. This arc length CD will be equal to arc length C prime D prime on the xy plane, where theta is equal to pi by 2. So C prime D prime you have written. Now what is C prime D prime? C prime D prime is, arc length C prime D prime is OC prime line, OC prime line segment. Line segment, straight line here means line segment. OC prime into angular displacement d phi on the xy plane. So OC prime, now let's see. But what is this OC prime? OC prime is the shadow of OC. And that shadow is equal to line segment OC times sine theta d theta. This angle is OC is making an angle of theta plus d theta with respect to the z-axis, sine theta d theta. And OC is equal to R plus dr. Therefore, arc length C prime d prime, which has been written over here, will be written as OC prime, and OC prime is R plus dr sine of theta plus d theta. You can just do something. Once you have got this formula, you can just work on some familiar trigonometric rules. dr goes to 0, d theta goes to 0. So keeping just only one d. After all, you are dealing with a line element, and line element to a first order can only keep one d. This thing is going to a very small value, this thing is going to a very small value, this thing is going to a very small value. But this thing can be neglected against r, and this d theta can be neglected against theta. D phi has nothing against which it can be neglected. That's why you have to keep it. And so basically this r plus dr will become r. and sine of theta plus d theta will become sine theta. You can expand it, sine theta cos d theta plus cos theta sine d theta. So cos of d theta will become 1, that is sine theta, and sine of d theta will become equal to d theta, that going to 0, you can drop this term, and that the whole thing will become sine theta. So that is to a first order, you get this thing. Vectorially, the outer arc length, having the length dimension, c prime d prime, will be r sine theta d phi vectorially, and there will be a phi cap. Okay, two last points to discuss over here quickly. Surface and volume elements of a sphere. This is a particularly important discussion. I wonder whether I'd be able to finish it within today, but let's see. I told you that two things are very important in spherical polar coordinate system, the open outer face and the volume element. Open outer face gives you the full surface area of a sphere. Let's see. The area element of the open outer face, refer to the main set of notes, which I finished discussing a while ago, is r squared sine theta d phi r cap. Total area will be r squared. Sine theta d theta, area meaning you have to carry out two integrals, d theta d phi. Sine theta d theta and d phi r cap. 0 to 2 pi. Now, something very important. Please be attentive. Unless otherwise mentioned, these are the limits of the theta and the phi integrals, and that is something you shall always have to do. Theta is to be integrated not from 0 to pi and not from 0 to 2 pi, meaning don't start here, come down here, and then go up again. Theta is a half, theta will be defined by this half circle, whereas phi will be defined by this full circle. Phi will go over the limit of 0 to 2 pi by a full cycle or circle over a full circle, but theta over only one half circle. Why? I shall argue soon enough. So you will get r squared, integral of sine theta will be minus cos theta 0 to pi, and then d phi will give you 2 pi r cap. That is what you have, and then cos theta, well, I mean, this minus is coming out. Cos of pi will be minus 1, cos of 0 will be 1, so minus 1 of minus 1 will be minus 2, and there's this minus sign already, which is out here, so minus 2 into minus 1 will be plus 2. And this integrated from 0 to 2 pi will just give you 2 pi. That's very simple. So 4 pi r squared r cap. I hope you're familiar with this formula. That's the full surface area of a sphere. Now the next question, why theta is integrated from 0 to pi and not 2 pi? Please be attentive on this point. Many arguments. I'll first give you the simple algebraic argument. If the integral is from 0 to 2 pi, sine theta d theta going from 0 to 2 pi, then the integral will vanish. You can see that cos theta will be equal to 0. So, I'm sorry, cos theta will be equal to, cos of 0 will be equal to 1, and cos of 2 pi, which is also the same as 0, will be equal to 1, making the surface area go to 0. Okay, but that's just an algebraic argument. What's about a geometric intuition? Here, I'll just quickly finish this discussion. Here, suppose you start integrating from 0 to pi. Integrating from 0 to pi gives a half disk. I'm asking you to find out this shaded area. This phi goes from 0 to 2 pi, but theta gives you the half disk, right? As in the figure on the right. 0 to pi gives a half disk. If you had integrated from 0 to 2 pi, you would have got a full disk. But wait, we don't want the full disk. That will cause a problem for us. Why so? Because first integral is theta. Remember, theta is the second vector, phi is the third vector. So the first integration happens over theta. Theta comes before phi. So you integrate over theta from 0 to pi. Then you integrate over phi from 0 to 2 pi. And what is the integration over phi like? Geometrically, you follow this point carefully. Integration of phi is like taking this half disk and sweeping it out through space anti-clockwise like that. When the half, and sweeping it out through space means that this half disk is being rotated. Like it's just like a door, except that the door is not like a rectangle. What is the sweeping of a door like? A door sweeps through an angle of 90 degrees next to a wall or whatever. It's got a rectangular shape. So it'll sweep out a cylindrical kind of a configuration. But this is not a standard door. This is a half disk door. Just give me a minute. I'll finish this thing. This is a half disk door. and you're sweeping it over. It's just like a hard disk revolving door, right? Like you see in shopping malls or hotels, wherever. So half disk is rotated through 0 to 2 pi about the z-axis, hinged about this z-axis like a door. The half circumference traces out a surface that will be spherical. Now, geometrically, this is the important point I was trying to make. If a full disk were to be rotated, then one half of its circumference would have erased the surface, spherical surface traced out by the other half. So the first half would have traced out a spherical surface, and then the second half on the other side would have erased that. That is what you get algebraically over here. Anyway, if you don't want to get into all this complicated understanding of all that, not to worry, just drill it into your head that whenever a surface integral, whenever an integral comes, R integral has to be done first. In this case, there is no R integral, but there is a theta and a phi integral. So the second coordinate is theta, therefore its integral has to be computed first, then the third integral is phi. That integral has to be computed after. We just have to discuss the volume of a sphere. The volume of a sphere is going to give you this integral, will give you 4/3 pi r cubed, but we don't have time today. I will finish the discussion here on Monday, on next Wednesday, we will continue with the discussion, and also we shall start on electrostatics. I'm stopping the sharing now as well as the recording. If you have anything to ask me, you may please do so. Otherwise, we may end the session. I'm anyway stopping the recording.